All right, Joel. We'll see if anyone else shows up. But for the people in the video, I said I'm going to print you notes and the homework, and I'm not going to check the homework like for a grade, but it's good obviously for you to practice this stuff. It's like just taking the notes won't be enough practice. But here is the first unit that is BC only. This is when you can kind of notice a bit of a jump from AB to BC, because the stuff in Unit 9 is pretty abstract, and then the stuff in Unit 10 is like very far out there. Well, not like way out of reach, but it's a jump for sure from derivatives and integrals to series. It's kind of wild. But you'll see, you'll get there, you'll be fine. But first though is Unit 9, which is parametric equations and polar equations, which if you don't remember what that even is, we have like that built into this little package to like remind you of how these work. So parametric equations, what this little page says is that the functions that you guys are used to graphing are like x and y, like y equals function of x, y equals function of x, where you just like the x is the independent variable and then the y depends on that x. Like depending on what x you plug in, the y changes based on that. But sometimes you'll see why later, but sometimes it's useful or interesting or whatever to have both x and y change with respect to this invisible, somewhere in here, the hidden third variable, most often time. Again, you'll see applications of this like tomorrow or coming up at least. But yeah, sometimes you want to change x so that that's a function and y so that that's a function and see the combination of the two and see how that function behaves. But that's what's called a parametric equation. If x depends on time and y depends on time, and so you take them both together and you get a crazy looking path, that's what a parametric equation is. I would think that you have seen these before, but I might be wrong. Have you heard of these parametric equations where both x and y depend on t? That sounds familiar to you? Well, maybe after you see an example, you'll see it. But let me make sure I don't want to say anything else from this little intro. Hidden third variable, parameter, we can now examine. Oh, yeah, okay, maybe I'll say it, but you're about to see it in the example anyway. But right here it tells you that x will have its own function that depends on time, and y will have its own function that depends on time. And you figure out how those two are interacting by themselves, and then you graph them like together, and you'll see what I'm talking about when we do an example. But yeah, x will have its own function, y will have its own function, so they'll both behave in weird ways, and together they'll behave even weirder. But you'll see what I'm talking about, like I said, in a second. Those are called parametric equations, and t is called the parameter. And then here's something important too, is that sometimes you can express parametric equations as a normal function, but a lot of times you can't. That's the whole point of parametric equations, is that you can combine them. You can make this new crazy function, or not even a function. You can make this new crazy graph that you can't make if you just rely on like rectangular functions, y equals f of x. But when you can write the function, the parametric equations as a single y equals f of x function, then that's what's called eliminating a parameter. You'll see that in a second again. And then when graphing parametric equations, it's important to remember that you're still graphing along the x and y axis. Thus, when sketching a curve, oh, I'll tell you about that as we do it. But let's do an example so you can finally see what I'm talking about. I was thinking for sure you'd seen this before, but I guess you didn't see it in pre-calculus, which is sad news. But this should hopefully give you at least a little bit of an intro into what's going on. So it says, without a calculator, make a table, sketch the curve, and then indicate the direction, and then eliminate the parameter. So here's what it's asking. Make the graph of this relationship, this parametric equation. So not to make a graph like you know and love. And like I'm gonna do it the like what you learned way back in the day still applies, where you can make a little table with x's and y's and plot those points and connect them, and that's my graph. But like I said, now both x and, like it used to be that in algebra 1 or whatever, you'd choose the x's, you'd plug them in, and you'd find out what y is. Now you can't choose anything. You can't choose the x, can't choose the y. They both depend on this third variable t. So you have to make a 3 column table where the t is what you're choosing. That's the independent variable. And then x and y both depend on whatever you chose for t. And for a lot of these, we forgot to type it in, but this one does a good job of saying time goes between. T usually stands for time, and it says that t spans from -2 to 3. So let me just choose the easiest, the whole number between there. So -2, -1. Again, I'm choosing these based on the restriction that they gave me that I circled over there. -2, -1, 0, 1, and 2, and 3. And then I just plug these into the x function, I plug these into the y function, and then I'll have some x, y points to plug. So that looks like -2 into the x function would be, I gotta save some space for this last part, eliminating the parameter. But I'll show my work for the first couple, and then you'll get the idea. Here's me plugging into x, -2 into that would be -2 squared minus 4. It's 4 minus 4, which is 0, so that's my first x value. And then let me just focus on all the x's, then all the y's, and then I'll put them together. Then -1 squared would be the same thing. 1 minus 4 is -3. Then 0 minus 4 is -4. 1 minus 4, -3. 4 minus 4 is 0. And 9 minus 4 is 5. Too fast or fine? Okay. All right, and then do the same thing into y. So -2 over 2. Now I'm looking at this orange equation. That was the black equation. Here's the orange equation. To take -2 into there, y equals -2 over 2 is -1. So this guy is -1. And then same thing for, if I plug in -1, I get -1/2. I plug in 0, I get 0. I plug in 1, I get 1/2. Here's a new set of notes. When I say I plug in 1, I get 1/2. I plug in 2, I get 2 over 2 is 1. Plug in 3, I get 3/2, so 1.5. Yeah, I think 1.5 might make it easier to graph in a second, rather than 3/2, but whatever. It's all the same thing. Okay, and then now that you have a good set of points, you can kind of forget about the t and just plot these points. But the t does come back in a second in a weird way, but I'll talk about that in a sec. Small, get it out of the way of my graph. And then now I'll graph these. I wish they had given us a nice coordinate plane to graph on, but we can make our own. So on x, I need to go all the way from -4 to 5. So let me make my scale accordingly. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, and then on the y, I need to go from -1 is the lowest, and 1.5 is the biggest. So I'll make my 1 here, 2 here. This will be 1.5. This will be -1, -2. Cool. And then, like I said, now you're just plotting these points: 0, -1. That in green. 0, -1, green. Then the next point would be -3, -1/2. Whoop, whoop, right around here. Then -4, 0. -3, 1/2. Slow down in case you're totally lost, but I think you know what I'm doing. Okay, 0, 1, and 5, 1.5. Cool. And then connect them and keep track of the order in which you plotted them. Because of what I'm about to say. But let me connect them first. I connected them like this. And I need to indicate the order in which I connected them because, again, most of the time, T stands for time. So you kind of gotta know in which, like, as you plugged in bigger and bigger values of T, what happened to the graph? Like, where did the graph start at -2 and where did it go from there? Because this T is not clearly visible on the graph. You see what I'm saying? Like, it wouldn't show up on the graph if you didn't tell it where you started and where you ended. In other words, keep track of what the first point is and in which direction you move. That's what it's talking about when it says indicate the orientation. Those are the arrows. Cool. Okay. Okay. Are you good on the graphing bit? Kind of see how these are interesting. You get this interesting looking graph. Okay. And then the last bit, it says eliminate the parameter, which is why I told you to save room over here. What that means is write this as a normal equation, y equals blah, 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 x, or x equals blah, 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 y. So what, I mean, you can probably guess how I'm about to do that. Here's my two equations. If you were to guess how I'm going to make this an equation of just x's and y's, what would you think? You know?
You can put the y for c squared.
Yeah, exactly. Look at one of these will be pretty easy. Well, I mean, neither one of these is super hard to solve, but this one, this y one that I'm circling right here with my mouse, is easy to solve if I just go 2y equals t. And that guy is saying take that and plug that in for the t over here. Whoop, plus that, and then now you have only x. Now you have x equals not t squared, but 2y squared minus 4. And I mean, you did it. There it is. But if you want to make it look a little nicer, there you go. Now it's all x's and y's, a rectangular equation. You don't have to solve this one for y. In fact, it would be worse if you solved it for y, because then you'd make it two different. You make it a positive and a negative square root. Anyway, once you have all x's and y's, you're good. It's stop there. Cool. All right. You getting this? This making sense? All right, let me say that sometimes it's not possible to eliminate the parameter, but all three of these examples that we put on here, we made it so that it is possible to eliminate the parameter. But you get the most interesting graphs when you can't solve it for the parameter. So if I made up something crazy and put it into Desmos, you get some pretty neat graphs. Did I see a hand here or there? Okay, I made that up, I guess. All right, well, there you go. There's example 1. Okay, sorry, people in the video. I was like doing something in the class. But here's the next one. It says example 2, without a calculator. Oh, do the same thing. Yeah, all three of these are the same thing now that I think back. So all right, let's do it. Same thing. I make a three-way table. It says T, X, and Y. The T you get oh, I forgot that this one doesn't tell you like where T ranges from. And it should, like that's a typo. That's not something you have to figure out. So I said for convenience, this would be undefined. This X equation would be undefined if we chose numbers smaller than 1. So I said go from, let me check my key. I said 1 to, maybe I didn't even give it a number bound. Yeah, I just said make T be bigger than 1, or like at least 1. Okay, so for T, I'm just going to choose easy values of T. I'm going to choose 1. I'm going to choose 2. I'm going to choose maybe 3. But if I'm thinking ahead, that would give me a square root of 2, which doesn't like tell me that much. So I'm going to choose easy values for this. So I chose 1, 2, 5 would be an easy square root. 10 would be an easy square root, and that might be enough. But like 1 more, 17 would be an easy square root. And then, oh hello.
Where's your breakfast?
Hey,
Cheddar or white?
what is it?
Fresh bagels, please. You need that?
Yeah,
What do you want? Cheddar or white? White.
cheddar.
Okay, so you roll.
Hey, let's do that later. Okay, now I'm just plugging these t's in. So 1, well, square root of 1 minus 1 again. All I'm doing is I'm taking these values, plugging them into each function. 1 minus 1 is 0, so square root of that is 0. 2 minus 1 is 1, square root of that is 1. 5 minus 1 is 4, square root of that is 2, etc. I think you guys can do the rest. And then for y would be 3, 4, 7, 12, 17. Okay. All right. And then now we can graph the points. Are you guys good? If I haven't checked on you guys, but I hope you're good. 0, 1, 2, 3, 4. I have to go all the way to 19. Okay. Okay. Cool. Okay, and then here's me graphing 0, 3. Oh. 0, 3. 1, 4. 2, 7. 3, 12. And if I made my if I had made my dots like my scale better, this would look a little bit better. But actually, let me not give away what it should have looked like originally, because you'll see once we eliminate the parameter. So there's my graph, but don't forget that you have to keep track of what point was first and where you go from there. So I went this way. Cool. And then here's us eliminating the parameter. There. Okay, eliminating the parameter. Here's our two equations. Obviously, the y one is easier to solve, so here's me solving that. Y minus 2 equals t. And now I take that into that t. And then that's a good answer for. There's a nice simplified answer. Cool. And then now you can see what I'm saying is this should look like half of a parabola since this is just the positive square root of y minus 3. If you were to solve that, you'd get like x squared plus 3, but only the positive half. So whoop, that's why that looks like that. Nice. And then the last one is more interesting. What questions on this one? Okay. Last one, unless I'm wrong. That's just how to put that into a calculator. All right, last one says the same thing, but now you got more interesting equation. And then again, we forgot to tell you like a restriction on t. So let me just use the most natural one. Since these are sines and cosines, let me just set a like a 0 to 2 pi restriction. And then for the sake of making this easy, I'm just going to choose the easiest, I'm just going to choose the axis values on the unit circle. And then if I need more detail, I'll fill in the pi over 4 and pi over 6 and all that stuff later. But you'll see that you don't even do that. So this is where I would start. The homework problem is I would say, okay, what's the easiest values to plug in? I said 0, pi over 2, pi, 3 pi over 2, and 2 pi. That would make my life easier. And then if I can't tell really what the graph is doing, okay, fine, I'll plug in the pi over 6 and the 2 pi over 6 and the pi over 4, all that stuff to get more detail. Okay, so here's us doing that. Well, let me check on you guys. You guys remember the cosine of 0? Nice. Nice. Yeah, okay. Hopefully you said cosine of 0 is the x value on the unit circle. So cosine of 0 is 1. So 3 plus 2 would be 5. And then cosine of pi over 2 would be right here, which is 0. So 3 plus 0 is 0. Or sorry, 3 plus 0 is 3. Pi into this would give me 3 minus 2 because that's cosine right there, which is 1. And then 3 pi over 2 is 0 again. So 3 plus 0 is 3. And 2 pi gets me back to 5. And then on the y, similar thing, -1 plus sine of 0 is now 0, so -1. -1 plus 3 is 2. -1 plus 0 is -1. 3 pi over 2 is down here, so -1 minus 3 is -4, and 2 pi gets me -1 again. Yeah? Okay. All right. Then here's us graphing this one. We go 3, 4, 5, and then -4 to 2. That's not bad. Okay. 1, 2, 3, 4, 5. And then -1. Okay. And then let us graph that. So 5, -1 here. 3, 2 here. 1, -1 here. 3, 4. No, 3, -4. Here, back to this. So what we got is this shape. If you wanted more detail, you could, like I said, you could plug in points in between to see if this is really what's going on. But you'll see why I'm very confident that this is an oval, an ellipse, once we eliminate the parameter. But don't forget, don't only connect it, but remember that you started at 5, -1, and you went around this way. Put in the little arrows to indicate which way you go. Nice. Okay, and then eliminating the parameter for this one is kind of wild. This is why I said this one is is interesting because this one's kind of cool. If there's a sine and a cosine, if one of the x's is sine, one of x and y is sine, and the other one is cosine, then you can use this neat little trick instead of getting like. If you look ahead, if you were trying to solve this like normal, you'd subtract 3, divide by 2, and then take the inverse cosine. And then plugging that into this t, you'd get a 3 sine of inverse cosine of crazy stuff. The nicer thing to do is watch this, guys. Watch this. There's my x. Here's my y. What you can do is take advantage of the trig identities that you learned last year in pre-calculus and only solve for cosine and sine. Like I'm gonna make this not say t equals whatever, but cosine of t equals whatever. So here is this one in black. That would be x minus 3 equals 2 cosine of t, which means that x minus 3 over 2 equals cosine of t, and stop there. And then I'm going to solve this green one for sine only. So y plus 1 equals 3 sine of t, meaning that y plus 1 over 3 equals sine of t. And then take advantage of the fact, here's my 2 relevant equations. Take advantage of the fact that sine squared plus cosine squared is always 1. And since you have a cosine here and a sine here, you can just square each of these and make that equal 1. And that's the neat little trick that you can do. So my final answer would look like x squared. Well, I'm going to put the cosine first because that's the first one I called for. So x minus 3 over 2 squared plus y plus 1 over 3 squared equals 1. And now you've done it. Now there's no t's in it. Which is, well, you guys see ellipses before? You guys remember that this is an ellipse? Like ellipses should look like circles, but they're fractions instead of, and they're different like denominators down here. I don't know how much you remember about ellipses or whatever, but this should be an ellipse centered at 3, -1. Right there's the center, and you go 2 across on the x-axis, and you go 3 up on the y-axis, and there's your ellipse. I don't know if you remember that. It's looking like you don't remember ellipses that much, but yeah, if you can take my word for it, that's the equation for an ellipse. Cool. So kind of interesting. How important is this on the AP test that you understand this little trick? Not that important. This is really just none of this will be on the AP test. It's more like the calculus of this, taking derivatives and integrals of this will be on the AP test. But if you don't understand how parametric equations work, then that can be pretty confusing. So this was an intro into here's how parametric equations work and act and why they're interesting. And then tomorrow you'll see more. Well, Monday you'll see more of the calculus side of it. Cool. So that's the work we got to do. Then this right here, if you have a TI calculator, tells you how to put in parametric equations. But most of you guys will probably be using Desmos. So let me show you real quick how to put this in Desmos. In fact, let me just write it here so you can see. That in Desmos, you'll just put in the x equation and the y equation separated by a comma. So like, look, let me show you. I'm gonna make this small over here, and then I'll pull up Desmos here. And I'll show you that, of course, you know, to put in a point, you put x comma y, and that puts that red point there. But you can also put full function of x and oh, that's not what I wanted. The Earth. Rats. I don't know how I did that. Now I can't get out of it.
That's not 11.
S11. Job. Okay, like I said, put in points and you get a point. Put in a function and it interprets it the way you want it. So you want, I'm about to put in this equation and see if we get this little loop. The equation should be 3t. I'm just gonna put this in. Just notice that a is 1. 3t over what? Oh, over 1 plus t cubed, comma, 3t squared over 1 plus t cubed. And we don't get the loop, and that's because we didn't go far enough in the t direction. So let me change the t restrictions from -10 to 10 or something. And then you get that loop that they have here. Cool, and then that's true for all these other equations. So summary, if you want parametric equations, just put in x equation, comma, y equation, and you get it on there. Some of these are more interesting. Look at this one, is great. Question.
What is that A?
I don't know. I mean, maybe if you make it different, like maybe if I make A be 2, then I make this like 6 and 6. Then you get the same type of shape. I don't know. I haven't studied this much. Well, yeah, I'll just make it 10. As it just makes it bigger and bigger. Yeah, I don't know why there's an A and why that A matters. Well, maybe you. Other questions? Okay, if you want kind of an intuitive explanation of parametric equation, I have it for you 1v1. I can show you an intuitive example and you'll get a better understanding of it. But if you just want to know kind of the idea behind them, you just got it. It's like the x and the y both have their equations, and sometimes when you put it together, you get an interesting looking equation or graph out of that. All right. Good job, y'all. Homework tomorrow. I'll print your homework and give it to you Monday.